Yeah. So we start a new topic, inverter-based amplifier. This inverter is a CMOS inverter. This inverter. See? Yeah, that's CMOS inverter. How come we can use this CMOS inverter as an amplifier? Yeah, see, if both transistors work in a saturation region, actually, yeah, the small signal voltage gain will be, at the low frequency will be GMN plus GMP times RO and parallel ROP, okay? So if they work in the saturation region, this RO is large, and this GM is also large. We have a very large voltage gain if both transistors work in saturation region, okay? And then this amp has some advantage and some disadvantage. Okay, the advantage of this CMOS inverter is it has a very small noise, low noise. So it is pretty fast. So it means, say, we can achieve very low power for some, if I reduce the operating frequency. So it works pretty fast and low power. You know, this low noise happens because low noise. Okay, let's talk about the low noise. Oops, how come? I need more spaces. Yeah, this GM, the total GM is sum of NMOS GM and PMOS GM, okay? And then the noise, this noise is noise current. There are some noise current here, okay? This noise current power equal 4 kT in saturation region. Ooh, I think this is something like that. This is a thermal noise. This is in the saturation region. Is it? Oh, should be GM, right? GM, GM, 4KTR of GM. Oh, sorry. This should be something like that. Yeah, this is power spectral density of noise current. All right. Equivalent input noise voltage will be just this GM square times this one, all right? Then this equivalent noise will be, something like that. Yeah. So we didn't talk about the Flicker noise. We just talk about the thermal noise. So this is GMN plus GMP times 4KT. Looks like those things gone. So, because this one reduces this VIEQ significantly. If you compare this one, simple differential pair, See, we talked about that. This is a conventional differential pair. We talked about that. Those M3 current, M3 transistor contribute to noise, right? They contribute to noise, but they don't contribute this GM, right? So here's this GM is small because this GM is only GM1, but this IN is say GM1, GM3 there, right? Okay. So it has this one has a much larger noise than this CMOS inverter. Yeah, this active load contribute to noise, not transconductance of this amplifier. Okay? Question?
근데 여기 GM 엔더하고 GM POD 중에 볼티지가 인풋 볼티지가 예를 들어서 합포 볼티지나 이런 근처면 VGS-VTH가 GM 값이 별로 그렇게 만약에 안 큰 거랑 비교해 보면은 누가 더 큰다고 그러니까 만약에 V가 굉장히 VGS 이게 인풋이 큰 때랑 이거 더한 거랑 두 값이 비슷할 수도 있는
I don't quite understand your question. Say you are talking about this GM value at this works at around the logic threshold. Okay, logic threshold is around half VDD. Okay, in a half VDD, let's just see. So you are talking about so this is around half VDD. This operating point, eh? Then this one may be some weak inversion or whatever, or some lower. So you said this is a small VGS minus VTH to increase the voltage gain, but this one has a large VGS minus VTH, right? So here, see, this one will generate I mean, both small GM, this is good. This is pretty large. I mean, both small VGS, not GM itself. The ratio is large, both small VGS minus VTH. Okay? Ratio. Yeah, this ratio thing is just, let's just see. I think this is ideal GM. Yeah, this is something like that. In strong inversion. In weak inversion, this is this one, right? Constant in weak inversion. But see, this ratio is good, but this GM is not pretty large here. For noise performance, this is no good. Noise performance. In noise performance, there is see here. This noise performance is VIEQN will be for this one, for that one. VIEQN will be something like GM1 square 4KT 2/3 something like GM1 GM3 something like that. Is this right? Yeah, something like that. So so we try to operate this one in a strong inversion, this one weak inversion, to reduce this GM3, right? We try that. So to reduce this noise, right? But here, see, we don't have to worry about that strong inversion, weak inversion stuff, because if I increase just the magnitude of GM, it will reduce noise, input noise voltage. Okay? Yeah. So this inverter is pretty good noise performance, inverter amplifier. However, it has some mismatch problem, like PVT. It's sensitive to PVT variation. So for example, see, if the DC transfer curve of this one will be pretty sharp, something like that. 0 VDD. Okay, 0 VDD. So we have to operate this one at the logic threshold, right? This logic threshold point. If there is some mismatch, shifted a little bit like a 10 millivolt, then I have my operating point goes here. Then I have very small gain only, right? So it's very sensitive to PVT variation, and also to this supply voltage, right? Yeah, mismatch. To avoid the mismatch problem, we can use a long L, long W, wide W, and long L. And then also it's sensitive to PSRR, power supply rejection. Then we need a LDO, the regulator for the VDD supply. Okay. Question? Nope. Okay, let's look at some. Before going into inverter amplifier, let's try to find the DC transfer curve. Yeah, this is only inverter, right? This sub-circuit is inverter. Say this thing is in out, right? In out, and then my PMOS is 3 by 1, NMOS is 1 by 1. So each length is larger than 0.35 micron, right? It's 1 micron to avoid, to reduce mismatch effect. So here, see, I used different supply voltages. So this X1 is my inverter, my supply voltage is 3 volt, and then this thing is a 2.5 volt, or 2 and 2 volt, and then so I have several different supply voltage up to 0.1, and see what happens in DC transfer curve. So here, let's just see. Oh, yeah. Where is my inverter? Oh yeah, inverter DC tran. This is the one. Okay, edit. You can see the same code here. Simulate. It shouldn't take this long. What happens? Oh, okay. This computer is just slow. Okay, yeah. Yeah, and then my output. Yeah, 3. This is for 3 volt VDD. This is for 2.5 volt VDD. Vout versus Vin. This is a 2 volt, 1.5, 1.5. Yeah, 1.0 VDD is 1 volt. This is 0.5 volt. This is 0.4 volt. 0.3 volt, 0.2 volt, 0.1 volt. Oh, say 0.5 volt looks okay, right? Say if I eliminate those things, this is 3 volt is eliminated, 2.5 eliminated, 2 volt eliminated, 1.5 volt eliminated. This is 1 volt eliminated. I have very large gain, right? This is 0.5. 0.5 looks okay, right? But 0.4, still looks okay. 0.3, not very good, right? 0.3, not so good. Yeah, we cannot use 0.1. So that's no good. Okay, I think it's safe to use VDD larger than or equal to 0.5 volt with this process. They work in a sub-threshold region. Okay, let's look at the AC gain. Where is my AC gain? Oh yeah, this is AC. In this AC, inside the sub-circuit, I use the capacitor coupling in input. Input is connected to huge capacitor, And then I have a feedback resistor, huge resistor to set logic threshold. I have a small load cap capacitor, 0.1 pop. And then I want to probe Bode plot at the different supply voltage, okay? So simulate. Yeah, then let's just see, where is AC? Oh yeah, this is my AC. Okay, then plot. Yeah, this is my magnitude at the, okay, let's put log here. Okay. This is, my DC gain is around 60 at the 3 volt, right? Is this 60 or 50, 54? 54. Okay, how about 2.5? 2.5. Oh, I have increased my DC gain 2.5. How come this is gone? Oh, linear. Oh yeah, there. 2.5 is something wrong there. Let's see. How come? Oh, this is very weird. Let's try again. Yeah, this is 3.0 VDD 3 volt. Then this is 2.5. Gain becomes larger. This is 1.5. 1.0. 1.0, 0.5, 0.4, 0.3, 0.2, 0. This should be 0.1, something wrong. Okay, let's put all those things here. Yeah, where is 3.0? Oh yeah, I have a small gain. Let me kill 3.0. Let's kill this 2.5. Let's kill 1.5. Yeah, gain is increased, right? As I reduce VDD. And then this is 1 volt, right? So this should be 0.5 volt, is it right? No? 1, 2, 3, 4, 5. Oh, this is 1 volt. 1 volt, with a VDD 1 volt, my DC gain is 130, pretty large. Okay, I kill 1 volt, is it right? Yeah, this is 1 volt. So this 0.5 is not very good, right? I have this is 1 hertz, even cutoff frequency lower than 1 hertz. So looks like 0.5 volt is no good in AC characteristic. So those things has much smaller gain. I mean, 0.1, 0.2, their gain is less than 1. Okay. So this is AC characteristic. It looks like my VDD must be larger than 1 volt for the proper operation. Okay. Question. Okay. Let's stop here.